Okay, welcome everyone to our retreat session today. Hopefully you guys have had a chance to go over the sessions from the Soma team. Try to get together with your groups today until mid next week or so, and then we will see by the end of next week if we can have an office hour with Alex and Jen from Soma.
Sorry,
Um,
I lost connection
and
for a while.
it's all good. Welcome back. So yeah, today's session is with Ying, who's going to speak about lookup implementations in Halo 2, and I believe she'll be talking about some of the new stuff. And Ying is one of the best, in my opinion, one of the best communicator in ZK, and one of those rare people who are fluent in both the theory and implementations. So we are lucky to have her. So Ying, welcome, and the mic is yours.
Thank you. Yeah, actually I might have to share my host screen. Um, oh. So, yeah, as Ali said, this talk is an overview of lookup argument implementations in Halo 2. And yeah, beyond the sort of first generation, like subset check, reordering based lookup arguments, we're also going to look at the newer ones based on log derivatives and GKR. So this is the agenda. We're going to start off with the motivating use cases, and then we'll disambiguate some terms. And then the bulk of this presentation is going to be an overview of how the lookup arguments work. And finally, we'll see some benchmarks from the implementations. And interrupt me at any time. So I've been thinking of the use cases in these four categories. So perhaps the most common ones are fixed lookups that are very structured and very decomposable. So here I'm using decomposable loosely. There's formal definitions of decomposable, especially in the Lasso paper, but what I mean by decomposable is loosely that the lookup table can be broken into smaller tables and then reassembled to give the final result. So this is true for range checks, for example, where you're just checking inclusion in some predefined range. It's also true for, say, bitwise operations like XOR and AND, where you can, look up subsets of the bit string and then compose the result. So these are fixed because they can be computed in advance and they never change regardless. So basically, you can enumerate all possible outputs for all possible inputs. There's another class of use cases that are not decomposable. So I call these monolithic. So basically, you can't break up these tables into smaller tables. Like, for example, if you're looking at RISC-V instructions, you can't look at like half an instruction and compose it with another half. Or some nonlinear functions like ReLU. You can't ReLU like the first half of a value and the second half and recompose that. So the third class that I think about is dynamic lookups that are monolithic. So dynamic here, it means that it's not possible to enumerate the whole mapping of the function. For example, SHA-256, you cannot enumerate 2 to the 256 possible inputs. And so basically the table of values is changing all the time, depending on the inputs. And another common sort of use for dynamic monolithic lookups is to break up large circuits into more modular subcircuits. So, for example, this is a pretty old diagram that illustrates how the privacy scaling explorations ZK EVM is architected. So yeah, there's certain subcircuits that just turn out the results of catch-up on input values, and then these can be consumed by other subcircuits that, for example, use it in computing a Merkle hash. And also, another use case here is memory checking in virtual machines. So given a list of reads and writes, so given a list of reads and writes, you can look up the reads and writes relevant to a particular instruction. Yeah. And this last quadrant here is the newest one. And I don't understand it that well yet. So this is, and also it's not decomposable in that strict lasso definition. But basically this was proposed in the recent paper called Proofs for Deep Thought. And what they do is they create an accumulation scheme for memory checking. So it is like the memory checking in the previous case, except that it's carried out across multiple accumulation steps. And at each step, you're really only looking at a constant number of reads and writes. So in that sense, it's decomposable across accumulation steps. And this leads to some interesting optimizations. So I'm going to pause here for questions.
Anyone feel free to speak up or type it in the chat and I'll...
Yeah, so basically these are the use cases. You can understand them. Another way to understand them is basically you're either looking up deterministic computations or you're looking up memory. Like these are the two use cases where I see lookups being used.
There's a question, Ying, about the approximate efficiency of each bots, basically.
Yeah, that's a good question because when we try to benchmark, which we'll get to at the end, it is difficult to do justice to each protocol outside of the use case that it was optimized for. And so over here, I've put what I think is the best in class lookup for each use case in the sense that these were optimized for the particular use case. And if we skip ahead a little bit, there's a lot of subtleties when it comes to benchmarking. Okay, here's the punchline. Like I said, yeah, if you're gonna bench CQ on like a small fixed table or a decomposable fixed table, then it will probably lose that to lasso because it was not optimized for that. It's also difficult to bench across, like, for example, something that was meant for an accumulation scheme versus something that wasn't. Because the accumulation scheme is still going to have an expensive final decider, but the point is you're supposed to use the cheap accumulation verifier many times. And then it's also difficult to bench across just very different primitives. So lookups that use univariate versus multilinear polynomials. Yeah. So benchmarking is hard, as we all know. But I've tried to list over here some common metrics that all these protocols seem to be interested in. So for as long as you're using multi-exp based polynomial commitment scheme, it matters a lot the size of the field elements that you're committing to. So yeah, when we're doing these scalar multiplications, we want field elements that are small. And if the values that we're looking at are, say, 32 bits, we don't want to pay for the full field element, 256 bits. So yeah, there's also just reducing the number of commitments. So for example, Lookup, even the naive version of Lookup halves the number of commitments that the prover needs to make compared to the Halo2 subset argument. So yeah, the number of commitments and the size of the commitments is very, it can make a huge difference in prover time. There's also sort of, the resources that your prover has. Does it have access to highly parallel infrastructure? And if so, you should use a protocol like GKR, SumCheck and GKR, which is way more parallel than, say, than FFT. And also, do you have access to, like, pre-processing, like some machine that could store a huge preprocessed string for you? So for CQ, for example, this could go up to like terabytes for a large enough table, like 2 to the 32. And you need somewhere to store that, and you need some way to access that. So some kind of service. So yeah, the long story is that benchmarks are not always meaningful, equally meaningful for all contexts, and yeah, you should pick according to your use case. Now that being said, this is a benchmark that I got from Dohun's repo, where he's running 128 bit. Wait, let me see what exactly we're benching here. But I think it's 128 bit range check. Let me just check here. Yeah, 128 bit range check. So this is a good range check for to compare Lasso against the other protocols, because Lasso shines when there's a decomposable tables. So yeah, you can see here that the vanilla Halo2 lookup is the slowest, followed by MV lookup, which is, we'll see later, uses the lock derivative identity, but with the normal polynomial identity check, and for univariate polynomials. So that comes in second. About, so from 80 to 60. Yeah, I mean, it reduces the number of commitments that the prover has to make. And then we have Lookup, which is like MV lookup, but for multilinear polynomials. So for Lookup, you can't use it with the you can't just drop it into Halo2 like MV lookup. You have to, I think they used Lookup with Hyperplonk, which is multilinear. And then Lookup GKR is, it's like Lookup, but it uses GKR to check the final, to prove the final sum check. And it saves the prover from having to provide a bunch of so-called helper polynomials. So that's even fewer polynomial commitments. So Lookup GKR does better than Lookup. And it does equally well as Lasso over here. And yeah, I was surprised that it does exactly the same performance as Lasso. But on the other hand, it might not be so surprising because Lasso also uses GKR in the backend to for their grand product argument. So yeah, I kind of skipped to the punchline of the presentation, but that's it was a good question about, yeah, benchmarks, efficiency, and how to decide which lookup to use. So yeah, are there any other questions? Right. So now that we've gone through some use cases and had a preview of the benchmarks across like different protocols that are optimized for different use cases, we can move into the second part of the presentation, which is sort of a disambiguation of terms. So I think when I was reading these newer protocols, a lot of them are in the context of virtual machine and memory checking arguments, which are slightly different from lookup arguments. And both of these sometimes make use of multi-set equality arguments, which are again different. So for me, it was helpful to get the exact differences clear. So multi-set equality is sort of the basic building block, which are used in pretty much all of these lookup and memory checking arguments. So it's just a way to prove that some multi-set A is a permutation of another multi-set B. And how you do that is by taking a so-called permutation invariant fingerprint of multi-set A as well as multi-set B, and checking that these fingerprints match. So a multi-set equality can also be seen as a very, very special case of a lookup where the size of the input is exactly the size of the table, right? They have the same number of elements. But But a caveat here is that wrap it up generalizes the multi-set equality to work across different evaluation domains. And yeah, and what it does is basically introduces selectors that zero out parts of the parts of each multi-set that are irrelevant. So, sort of an if you've read Lasso or this Proofs for Deep Thought paper, you would see this term index lookup. It's a lookup with some additional restrictions. So basically, it's a lookup that specifies the index of the input in the table. So for a normal lookup, if we sort of shuffled the input, the lookup would still pass because it would still hold true that every element in the input appears somewhere in the table. And the point is we don't care where. Whereas for an indexed lookup, we have to specify where exactly in the table each element of the input appears. And so if we shuffle the input in an index lookup, then the original the positions that we committed to would no longer be valid. And lastly, so an index lookup can be considered a very special case of memory checking argument. So the JOLT paper says that if your memory checking argument is for read-only memories, then you can consider the index lookup as a memory checking argument. But if in general, memory checking arguments require the ability to write to the memory. So another way of using a lookup argument as a memory checking argument is if you provide the whole trace of the memory. So reads and writes across all time steps in one big table. But if you're going to be reading and writing dynamically, and if you're going to be changing the lookup table, then a simple index lookup would not suffice. So we're going to look at this, how to use a lookup argument for memory checking in the next slide. But before that, are there any questions? I don't know if it's just me who got confused with all these terms, but when I was reading the Proofs for Deep Thought paper, I thought there were good definitions for these. So, yeah, I mentioned previously that if we provide all reads and writes across all time steps in the memory trace, then we can use a simple lookup argument for memory checking. And this is what is done in many ZK EVM designs right now. So basically, you have one ordering of the memory trace that is time ordered. And then you have another ordering that is address ordered. And the rationale for ordering them differently is that in the time ordered version, you can check that the values were updated correctly according to certain instructions defined by the VM. Whereas in the address ordered version, you can check that the memory access, each read and write was a legal memory access, and that across the time steps, you didn't update the memory illegally. So yeah, these are some examples of what's a legal way to update memory. And then we can just prove a multi-set equality between these two orderings of the execution. And in this way, check that the check that the memory accesses in our execution are all the result of legal updates to the memory. So I think this should look pretty familiar to all of us. Are there any questions?
There is a question about examples. I guess this is an example of the multi-set equality, but for the other outer stuff like the indexed
Yeah.
lookup, what would be an intuitive example of that?
So the index lookup is actually let me see over here. So right. So how to build a memory checking argument using an index lookup? Okay. Yeah, I think so. The example I have here is how this is basically this is taken from a figure in Lasso's directory, and this is how they're using a memory checking argument internally in their lookup argument. So the direction is like flipped a little bit. But let me think. Yeah, I got confused about whether we're using a lookup for a memory checking argument or we're using a memory checking argument for a lookup. So okay, Lasso internally uses the spice memory checking argument. So Lasso is a lookup argument that internally uses a memory checking argument, which is this example that I have next. And then Jolt uses the Lasso lookup for its instructions, its VM instructions, and it uses the spice memory checking argument directly for memory checking. So if the question was about this comment here, about how a lookup argument for index lookups is equivalent to memcheck for read-only memories, basically how to understand this comment is that a read-only memory does not require the ability to update the memory. So you're only ever proving inclusion in a static list. And therefore, a lookup argument would suffice. A lookup argument here would be equivalent to memcheck for read-only memories. So actually, yeah, let's go through this example. This is how Lasso, the lookup argument, internally uses a memory checking argument. So so the lookup that we want to do is range check. So over here, we want to prove inclusion in a range of 16-bit values. So we initialize these values as entries in a read-only memory. So your read-only memory has values from 0 to 2 to the 16 minus 1. And these values are just equivalent to their address, by the way, in the memory. So this is a boring example. And you initialize all the counters to 0. So the counters count the number of reads and writes. And since this is read-only, it just counts the number of reads. So, sorry. Yeah, this is read-only, so it counts the number of reads. But conceptually, every time we do a read, we also do a virtual write that simply increments the counter, but it never changes the value in this specific case. So yeah, each time we do a lookup, we append, we change the counter and we append it to a set of reads and writes. So R and W are the read set and write set that increments with each lookup. And so after we're done with all our lookups, we'll end up with this final state of the table where, the only thing that's changed is the counters. It's the number of times we've looked up a certain value. So the actual values and the memory addresses don't ever change. And then, so how we use this memory checking argument as a lookup is that we check the following invariant, that the set of initial writes union the set of writes is equal to the set of reads union the final read. So everything that you read, you must have written at some point. And so if this memory checking invariant holds true, then the lookup argument holds true. Like every value that you looked up was indeed inside this read-only memory. Okay, are there any questions? So, by the way, I encourage everyone to look up this video by A16Z going through this Excalibur. So this is where, they break down how the lasso lookup internally uses memory checking. We'll also go through this in more detail in part 3. But this is really what motivated me to have a disambiguation section. I think, some of these are like special cases of some of the others, and some of these are used within some of the others. So the point is not really to get caught up in the definitions, but at the same time, it's to recognize that basically lookups are not all there is. And specifically in the context of memory checking, if we're just using a lookup argument, then we're sort of limited to a read-only memory, or we're limited to a representation of a memory that includes like the memory across all time steps. So it's a more inefficient way to do memory checking. Um, Whereas the general memory checking argument requires the ability to update the lookup, so to update the table. So it would require, so basically it would not work in the pre-processing setting that Lasso and CQ are optimized for.
I'm trying to think, Yang, if the indexed lookup is special case of lookup, or
Or
right
the
now you
other,
have it the other way. Yeah.
yeah, yeah. I was also thinking a lot of that because every indexed lookup is a lookup, but not every lookup is an index lookup. So in that sense, index lookup is a special case. Um, yeah, I flipped like the direction of this diagram like 3 times. Um, but another way to interpret this diagram is like what's more powerful. So in the sense that like I could implement a lookup using an index lookup. And I could implement a multi-set equality using a lookup, you see. But basically each of the smaller things is not like as powerful as the bigger thing. Yeah.
Yeah, I think
I
that makes sense. This graph reminds me of complexity classes, so thinking in terms of power might be a good
yeah.
way of.
Yeah. So I guess think of this in terms of power and not what's more general or what's a special case.
Yeah, that makes sense.
Okay. So this is all like just preface and motivation. So with the remaining 20 minutes, we can go through an overview of lookup arguments. So I assume, oh, right. Yeah, this timeline is really always evolving. Um, so, yeah, just for a bit of context, in 2022, we got Calc Plus, Calc and Calc Plus. So Calc Plus was groundbreaking in the sense that it it gave us a privilege whose work was independent of the size of the table. Whereas previously, for say Halo2 or Lookup, the prover had to process the whole table. Um, so yeah, but it's important to note that Calc Plus achieves this only in the pre-processing setting. Yeah. So since the tables are fixed, we can pre-compute a lot of information that the prover that we can offload that from the prover. So the most recent proofs for deep thought paper makes the prover work independent even in the dynamic setting. So even if your table is not fixed and you can't do any pre-processing, you can still get a prover that's independent of table size. So, but it's important to note here that they mean the accumulation prover. So in the context of an accumulation scheme, at each step, at each recursive step, the prover's work is only is a function only of the reads and writes in that step, and it's independent of the memory that's carried across all the steps. Yeah. So this table is also pretty old. It was adapted from CQ. So CQ is here. So this table doesn't include lasso or proofs for deep thought. But yeah, this table shows you the point at which this big N, which is the size of the table, disappears from the prover work. So in Calc Plus, the prover only pays like OM squared, M being the number of lookups, the number of inputs. And by the time we get to CQ, the prover only pays M log M in field operations and 8M group operations. Yeah, so we have to update this for lasso and mem update, but the difficulty is that both of lasso and mem update are kind of decomposable. So in a loose sense. So lasso breaks up. In CQ, we have one large table. In lasso, we would break that down into many small ones. So what should we bench here for prover work? And yeah, in the proofs for deep thought, we're kind of breaking it down across each accumulation step. So yeah, should we bench the accumulation prover here? So those were some difficulties that I ran into when trying to update this table. So we're gonna go over the vanilla Halo2 argument, and then we're gonna go over these three which have implementations in Halo2. Yeah. So okay, let's skip this for now. I think Halo2 lookup should be very familiar to all of us. So given some input, we want to prove that each element in the input appears somewhere in the table. And to do this, we create permuted versions of both the input and the table and check that indeed they were legal permutations, like actual permutations of the original. And then we check for the permuted input that we've permuted it in such a way that all the like values in the input are adjacent. And then we check that each first occurrence of a value in the permuted input is aligned with the same value in the permuted table. And these are the polynomial identities enforcing these conditions. So these polynomial identities are then just checked using the normal Halo2 IOP. Yeah, and so the drawback to this approach is, first of all, we have these two extra commitments to make. We need to commit the permuted input and permuted table. And that secondly, we need to pay the cost of the table. So yeah, these two reasons are sort of why Halo2 lookup has fallen behind the newer ones. So yeah. a more recent lookup argument is lookup that uses, so instead of using the multi-set equality in the product form, it uses the logarithmic derivative form that converts the identity to a sum. And so so what this allows us to do is in the context of Halo2, it allows us to get rid of these two extra permuted columns, and instead just provide one extra multiplicity column. And that essentially halves the number of commitments that the lookup prover needs to provide. So a recent improvement to lookup sort of so this thing I've linked here is lookup in its most naive form. So it's using univariate polynomials, and it's proving this sum check identity using a normal polynomial identity. Whereas a recent improvement to this scheme sort of directly proves this identity using the GKR protocol. And there's no need to provide these helper polynomials, and there's no need to commit to these helper polynomials. And so if you recall in our benchmarks, the difference between MV lookup and lookup GKR is really huge. I'm gonna pause for questions because I haven't done that in some time.
It seems no questions for now.
Okay. So sort of building on this log derivative form that was discovered in that was used in lookup, we have CQ that is highly optimized for the pre-processing setting, where we can pre-compute a lot of information about a potentially huge fixed table. So again, this identity here is the log derivative identity. And what CQ does is that it it works with this identity in the commitment space. And instead of directly working with so the plain values of the table, it just works with sorry, let me take a step back. So instead of considering the whole table, it allows the prover to consider only the elements of the table that are used. And yeah, this is because it does not work with the table size polynomial directly, and instead it only works with the commitments to these polynomials. And so if you try to compute the polynomial itself, it would take basically the time that would take would depend on the size of the actual table. Whereas if you compute just the commitments to the table, you only need to care about the elements of the table that you actually use. So yeah, I think I tried to explain that too vaguely. But that's the intuition behind it. That you can pre-compute all the commitments to the table that you would ever need, and then each time you're looking at elements of the table, you need to only access the elements that appear in your input. So that's how CQ sort of achieves a prover that's independent of the table size, even if the table is really huge. So yeah, we actually did implement CQ in Halo 2. But there are no meaningful benchmarks for it so far because we couldn't or we haven't yet set up like a server that's large enough to store all these pre-computed quotients. And yeah, to run this in production, we would need a server like that, and yeah, we would need it to be always running for any prover to query their relevant cast quotients that they need. Another thing to note is that CQ is optimized for very large tables that are hard to decompose. So yeah, it's also difficult to benchmark it against any of these other schemes. Yeah, but nonetheless, I think a meaningful benchmark for CQ would be if we implement the same function using two different approaches. So like if we had access to a huge table, maybe we could implement, say, SHA-256 way more efficiently versus using many smaller tables. So yeah, if anyone has ideas on sort of actually meaningful use cases that we could bench CQ on, do let me know. So yeah, what I would probably bench CQ against is Lasso. Because yeah, Lasso is also optimized for very large fixed tables that are decomposable. And Yeah, so lasso is the last argument that we're going to cover here. So we had seen previously already that lasso internally uses a memory checking argument. And now we're going to see it in the larger context. So yeah, the lasso lookup argument is proving that the elements of an input A appear somewhere in a lookup table T. And this is an index lookup argument, so you do specify exactly where in the table they appear. So yeah, I encourage you once again to watch the talk by A16Z, where you'll see that lasso is just a thin wrapper around a polynomial commitment scheme surge. And surge is where that memory checking argument that we saw previously appears. So yeah, surge is actually the memory checking argument is actually used to prove that we correctly indexed into the lookup table. So I'm not gonna get into the details over here, but I just wanted to note here that this memory checking invariant is also proven in search using this GKR grand product argument. So this should remind you of logup GKR, where they are proving the log derivative identity using GKR. And in both of these cases, you get the benefits of not having to commit to extra helper polynomials. So that's some intuition as to why both logup GKR and lasso are really fast. Yeah, that's all I had. Are there any questions?
One question from Nago says, what kind of properties or key aspects that a use case should have for creating or running benchmarks? I guess you touched upon this, Ying, but you can expand on it a bit.
Yeah. Yeah, I think it always makes sense to start with your use case. So, most of these use cases, I will say, are for virtual machines. And as we mentioned previously, lookups in the context of virtual machines are used to reduce the cost of non-native instructions like bit operations or SHA-256 or nonlinear functions. And they're also related to the memory checking arguments that are used in virtual machines. So, yeah. Yeah, it's a hard question to answer because even if we narrowed it down to a specific use case, there still remains like the resources and the limitations that you have. So I think CQ is a good example. If you don't have access to such a server or a service, then there's no point even starting. Yeah, and another consideration is also what assumptions you want to introduce. So CQ uses pairings, for example, whereas you might be trying to avoid that and just trying to stick to like phi, for example. Um, and if you're using a polynomial commitment scheme that's not homomorphic, then that might exclude this whole class of accumulation scheme lookup arguments optimized for accumulation schemes. So yeah, to me it's an open question basically, like how to fairly benchmark lookup arguments. And where I'm at right now is basically just use the lookup argument that's optimized for your use case.
In terms of swapping one lookup implementation for another, how much work does go into that in Halo 2 specifically? Like, what are the abstractions there?
Yeah, I think so. Um, yeah, from the experience I've had, um, there's kind of the main. There's two main changes that one could make. The first is the polynomial commitment scheme. So univariate versus multilinear. So yeah, Halo 2 lookup and MV lookup here were both univariate. And so that substitution was very easy. The API didn't change at all. Whereas logup and logup GKR were multilinear. And so yeah, they had to use hyperplonk. They had to use a different arithmetization. So that was a way more invasive change. Um, so that's the first kind of deep change. The second is basically whether or not you need to support pairings. So this is very CQ specific. When we implemented CQ, we had to break the abstraction over polynomial commitment schemes because CQ just would not work with anything besides KZG. And so right now, the CQ implementation is not compatible with any of the other Halo 2 forks. In terms of the traits, it just doesn't have an abstraction over polynomial commitment schemes. So yeah. Also, the Halo 2 library right now. There is no one canonical Halo 2 library. There's many different forks. And I think right now the only thing that all of them have in common is the front end API. So I think if you're trying to implement one of these lookup arguments or substitute one of them, you would probably want to steer clear of changing the front end circuit API. And yeah, the goal here is that you want people who write their circuits in Halo 2 to be able to just port over their circuits without changing anything. And yeah, that would keep you in the Halo 2 ecosystem. But besides the front end API, I don't think there's that much in common across different Halo 2 forks.
Putting our security glasses on, there is a question here from Nago. It says, in your experience, have you seen any exploits or vulnerabilities related to inefficiencies or lack thereof of real benchmarks? We can also generalize that question of, caveats to think about or easy ways of shooting yourself in the foot when it comes to lookups.
I see. Well, all of these implementations that I've shown are experimental. Yeah, whereas the Halo2 lookup, this slow one, uh, it has a security proof. It's been analyzed as part of the Halo2 protocol. So yeah, implementation wise, a lot of these are probably very buggy. And in fact, this MV lookup one, the last time I checked, it doesn't work with the IPA commitment. It only works with KZG. But that's an implementation problem because in theory, it doesn't need KZG, unlike CQ. Yeah, the other more subtle problem could be zero knowledgeness. So a lot of these newer lookup arguments are not zero knowledge, or they don't prove zero knowledge. Yeah, whereas, for example, the Halo2 lookup, there were a bunch of modifications made to it in order to accommodate blinding factors. And this introduced a lot of the inefficiencies that are in it. So, yeah, I guess you could run into bugs both in implementation as well as on the protocol level, just losing zero knowledgeness. But in terms of completeness and soundness, I'm not as worried there, because these newer lookup protocols, they do prove completeness and soundness. Yeah, and they have good compilers that, for example, convert from multilinear to univariate PCS. Yeah, so those are the top two foot guns in my mind. But of course, there could be a bunch more that we don't know about.
Yeah, lookup strikes me as one of those things that are very suitable for fuzzing, just blasting it with fuzzing test and seeing if something breaks. We'll probably nudge fellows to think about this. Has there been an implementation of deep thought, by the way, yet?
Not that I know of. Yeah, not that I know of.
Yeah, if you think it's manageable for intermediate level ZK devs, we could probably create a bounty for this just to get a proof of concept out there. Because it sounds like an interesting new development.
Yeah, yeah. It's very interesting. I have to read the paper carefully, but there's a bunch of sort of independent results in the paper as well. So one insight that they had about GKR is that it can break the witness barrier, what they call it. So what they mean by that is that the prover for deterministic computations doesn't need to commit to the whole witness. It only needs to commit to the inputs and outputs. And they gave an example in their paper of how this can be applied to um, make scalar models more efficient. Um, yeah, so I don't know. We should check with the authors if they know of any implementation efforts, but a bounty sounds like a good idea.
All right, sounds good. I'll definitely follow up on that after the session. Any more questions for Yang before we wrap up? Okay, so it seems there are no more questions. So next week we will continue digging into the second iteration of Suma. I encourage you guys to work in groups, and then towards the end of the week we will have an office hour session, and then Leo from Powder Lab might come back with a pedagogical session as well, probably the week after that. Um, and yeah, today we are wrapping up. Thank you so much, Yang, for the amazing session as always. If for people who are watching this in the future, if you have questions, feel free to ask on Discord, and we'll try to answer. We can continue the conversation there. Yeah, thanks again, Yang. Thank you everyone for attending, and we will see you next week.
Thank you.